This very first statement means that a cubed is congruent to 1 mod p, okay? And moreover, it means that there's no smaller natural number with that property, okay? So a squared would not be congruent to 1, and a itself would not be congruent to 1, which turns out to be important here. So again, that's what we mean by order, okay? A cubed is congruent to 1 mod p, and 3 is the smallest natural number with that property. Now, what do we mean by the least positive residue? Let's just do a concrete example. What if we were considering 29 modulo 5? Okay, 29 mod 5. Now, the possible positive remainders of any number upon division by 5 would be 1, 2, 3, and 4, right? Okay, so 29 mod 5, the least positive residue, if you'll allow me to abbreviate, I'll call it the LPR, least positive residue. The least positive residue of 29 mod 5 equals 4, right? Again, if you divide 29 by 5, you get a remainder of 4 because 29 is 5 times 5. 5 times 5 plus 4, okay? Now let's solve the problem here. Now again, this very first statement is just directly from what I just mentioned to you up here about order. This very next statement here is just a factorization of a cubed minus 1. Now this characterization, congruent to 0 mod p, also can be written as p divides a minus 1 times the quantity a squared plus a plus 1. Now what we can surmise very quickly here is that p does not divide a minus 1. And we know that because think of this as a to the first, right? A to the first minus 1 can't be congruent to 1, right? All right. And so that means that the only possibility that we can have right here is p divides a squared plus a plus 1, but that's the very same thing as saying that a squared plus a plus 1 is congruent to 0, and of course it's mod p. I'll leave that out. It's congruent to 0. And again, folks, this is the very well-known result that if you have p divides a product, that means p must divide one or the other of the factors. Okay, so that implies that p divides a or p divides b, right? A composite number does not have that property, okay, but a prime number does, okay? And so that's what's going on right here. Because of the fact the order of a is a cubed, this part right here can't be equal to 0 because this part right here couldn't be congruent to 1 mod p, right? So that means that there's no choice but for p to divide this part right here, which is the same thing as saying p or a squared plus a plus 1 is congruent to 0. All right, I hope that was clear. All right, now, so we're looking for the least positive residue of a plus 1 quantity cubed. Now, so we appeal to the factorization or the trinomial expansion, if you want to call it that, or the binomial expansion with the power of 3 here. And when you expand this out, you get this well-known result. Now notice that a cubed is congruent to 1 by supposition, right? A cubed is congruent to 1. And we already have 1 right here, so that's where this 2 comes from, right? Okay, so that much is clear. That's just arithmetic and the fact that a cubed is congruent to 1, right? A cubed is congruent to 1 just by supposition. The order of a is 3, is the supposition. Okay. So we get this, and then a little bit of algebra here. So a plus 1 cubed, we write it this way in a very convenient fashion, right? Because we have just shown that a squared plus a plus 1 is congruent to 0. So you see this entire piece right here is going to be congruent to -1, right? This part goes away because this part is congruent to 0. We just demonstrated that by previous argument, okay? So this is congruent to -1, but unfortunately that's not a negative number, right? But this is also, just by basic properties of congruence, is congruent to p-1. P is certainly a multiple of itself, right? So this is congruent to p-1, and that means this is going to be, this is your answer. It's the least positive residue, okay? We'll call that the LPR, least positive residue. It really is just the remainder. And you know the remainders are always numbers less than or equal to p-1, okay? So the least positive residue, sorry about that. This should be least positive residue. Let me erase that. Okay, so this should be LPR right here, least positive residue. And we've finished what we set out to prove. That is the least positive residue. Now let's take a look at a concrete example. So we're dealing with a prime number 7, right? 4 cubed, it's easy to demonstrate that that's congruent to 7 because that would be 63. In other words, 7 does divide 63, right? 7 divides 63. All right, 4 cubed is 64. 64 minus 1 is 63, and 9 times 7 is 63, right? Okay, so 4 cubed is definitely congruent to 1 mod 7. And now we're supposed to show that it's congruent to 7 minus 1, which I've written down right over here. Okay, to make that clear, that should be enveloped in parentheses maybe. Okay, and again, this isn't too hard to prove. In other words, 7 divides 125 minus 6. Now 125 minus 6 is 119, and 7 times 17 is 119. Okay, so 7 divides 125 minus 6. I'll do that parenthetically. All right, and that's true since 7 times 17 is equal to 129. Okay, so there's one example that kind of a sanity check. 7 times 17 is 70 plus 49, which is 119. Okay, so again, concrete example, and hopefully this proof was adequate for you. This is a fairly basic number theory proof. A little bit of modular arithmetic in the definition of order were the main results.